So, a very good morning to all of you. I am Uma Sharma, Assistant Professor in EC Department of AKGC Ghaziabad. Today, we will discuss the important topic of Analog Circuit Design course, that is biasing schemes of BJT. So, in this lecture, we will discuss the basics of transistor. Then, we will discuss the BJT and its biasing schemes. Here we will also discuss the load line and the need of biasing. And in the next lecture, we will discuss the biasing of MOSFET. So here you can see that a transistor, which is a device that can used either as an amplifier or as a switch. So here you can see that BJT is of two types. One is NPN, second one is the PNP. So here you can see the symbol of NPN and PNP, bipolar junction transistor. Here there are three terminals: base, collector and emitter, and the direction of current in NPN transistor is from collector to emitter. So this this symbol represents the direction of current. Here the direction of current is from emitter to collector node. So here you can see that at the base node, this is the direction of current. So you can see the basic structure of NPN and PNP transistor. This is the combination of two PN junction transistors. So here this is one junction and this is the another junction, and junction 1 is known as base emitter junction and this junction is known as base collector junction. And when we will discuss the amplification of this amplification of the signal using bipolar junction transistor, in that case you should know what should be the biasing of base emitter junction and base collector junction. So in this lecture we will discuss the biasing schemes which are associated with the transistor. So basically for NPN transistor, the transistor is can be used as an amplifier and as a switch. So for switching operation, the transistor should be operate in the cutoff region and the saturation region, but for the amplification application, the transistor should be operate in the active region, and for the active region, the emitter base junction should be forward bias and the collector base junction should be reverse bias. So this thing you have to remember. So from this diagram, it is clearly visible that the emitter current, as I have already told you, the direction of current in NPN transistor is from collector to emitter node. So the total current emitter can be represented by IC plus IB. So here we should know what is the need of biasing. So for example, to any system, if you want to amplify a signal, let's say this is amplifier and you want to amplify this signal, that means you want this signal at the output. So definitely you have to give some energy to this block, and in our case this block is BJT. So that means if you want to amplify any signal, so we have to add some voltage source to supply the energy to the incoming signal, so that at the output we can get the amplified output. So this this additional supply voltage which is required for the proper amplification is known as bias voltage. So this is something like that. For a car, there is a requirement of petrol or fuel. So similarly, in our case, an amplifier requires some additional voltage so that the circuit can operate. So the biasing is basically a external voltage which is applied to the BJT to ensure the proper operation of the transistor. So if you want to design an amplifier, that means the transistor should work in the active region, and active region means emitter base junction should be forward bias and the collector base junction should be reverse bias. So for the biasing, it is a very small voltage which is given to the input of the BJT, and this voltage we don't want to amplify, but the voltage is required to amplify the incoming signal. So for the amplification there are two conditions, like input voltage should exceed the cut-in voltage so that the emitter base junction will be in forward bias mode. This is just to make emitter base junction in forward bias. This is the meaning of this sentence. Emitter base junction should be in forward bias. And second, the BJT should be operate in the active region. That means collector base junction should be in reverse bias. So if appropriate DC voltage and current are given to the BJT by the external sources so that the BJT operate in the active region, and if we superimpose the AC signal which is to be amplified, then this problem of poor amplification or no amplification can be avoided. So it is necessary to add some biasing scheme in the circuit so that the circuit can amplify the signal properly. So biasing basically, as we have already discussed, it is referred to the application of DC voltage which is to set up the operating points. This is the important word, that is operating point, which is also known as Q point, which we can find on the DC load line when we discuss the characteristic of the BJT. So it is required to select Q point properly, and we have to ensure that there is no shift because of change in any parameter in the operating point. If is there any change in the operating point, that means that will affect the quality of amplification. So once we select the operating point, we have to ensure that the operating point should be stabilized. So for that there are so many schemes by which we can stabilize the circuit amplification, because there are some important factor by which these point can vary, like beta variation may be there, like temperature variation can affect the operating points. So these are the important points, like the main factor which is temperature. If temperature increases, the value of ICE, which is the collector to emitter current, beta, which is the current gain of the amplifier, and VBE, which is the base to emitter voltage, gets affected, because these are the function of temperature. As we know that the ICBO, which is the reverse saturation current, this is the reverse saturation current, it gets double for every 10° rise in the temperature. So if we talk about the total current IC, which is the summation of collector current plus reverse saturation current. So if there is any change in ICBO, that can affect the value of operating point, that is the IC. And also the VBE, which is base to emitter voltage, it decreases by 2.5 millivolts for every 1° rise in the temperature. So if there is any decrement in the VBE with respect to increase in temperature, that will again affect the value of IC, which is your operating points. So we have to ensure that the operating point or the biasing scheme is to be selected such that can provide the maximum stabilization, so that we can get the better amplification. So there are so many techniques which are available. So in these are some important biasing schemes. One is base resistor method, second one is the emitter bias, third one is the biasing with the collector feedback, and the voltage divider biasing. These are the methods by which we can obtain the value of operating points. And here one more thing, that in many circuits we can use two DC sources for biasing purpose. One is VVV and second one is the VCC. Whereas in our case we will consider only single supply circuits. So we will study all these biasing techniques based on the single supply. So other terminal, which is VVV, will be at the zero potential. But you can design the biasing techniques using the two supply methods also. So this is the first one, which is fixed biasing. So here we have considered the common emitter configuration. Because common emitter configuration provide the maximum amplification, current amplification. So because of this reason we have selected common emitter configuration. Otherwise you can select any circuit, that may be common base configuration or common collector configuration. These biasing techniques and schemes are valid for all the configuration. For the better understanding, and we already aware that we get the good amplification factor in case of common emitter configuration. That's why we have selected this configuration. So in common emitter configuration, you can see in this diagram, the emitter terminal is grounded. The input is applied at the base terminal, that is AC input signal, which is coupled through a coupling capacitor CC1 at the base node, and the base node is directly connected to supply to provide the biasing. Here the fixed resistance RB is used to provide the biasing to this circuit. The resistance is connected at the collector node, and at the collector node we will get the output through this coupling capacitor CC2. So when we are talking about the DC, because biasing means DC supply, biasing is exactly related to DC analysis only. There is with the help of biasing you can set the DC parameters only. So when we are talking about the DC analysis, you can see that the impedance across this capacitor will be very high because frequency is 0. So 1 upon 2 pi Fc will equals to infinite if F equals to 0. So this can be replaced by a open circuit. So this capacitor is now open circuited. Similarly, this capacitor CC2 is also open circuited. So from this explanation, you can understand in DC biasing there is no effect of the applied input signal. The whatever you apply at the input terminal, if you are doing the DC biasing, there is no effect of this input signal on your operating point, because this coupling capacitors are used to block the AC. So here you can see that for the DC DC analysis, the circuit is only this part. This is the circuit for DC biasing. In this box you can see that this is a circuit for DC biasing, fixed biasing. So now for this circuit we have to calculate the operating point. So the first step, we have to replace all the capacitor with the open circuit, and second step, we have to identify the two loop in which we can apply the KBL and we can calculate the value of IC and VCE. So here in our case there are two loops. One is, maybe I should change the color of pan. So one loop is this and another loop is this. So we can apply KBL in these two loops and calculate the value of IB. So let's see, in that case if we apply KBL at the input side, which is VE loop, so the equation will be VCC minus IB RB minus VBE equals to 0. So from here your IB will equals to VCC minus VBE divided by RB. So here you can see that this is your value of base current IB, And as you already know the relation between IC and IB, that is IC is beta times of IB. So this is how you can calculate the value of IC. So this is one of the operating point, because operating point means we have to calculate the output current and the output voltage. So now if we apply KVL at the second loop, which is the collector emitter loop, so you can write the equation VCC minus IC RC minus VCE equals to 0. So from here your VCE equals to VCC minus IC RC. So if you have already calculated the IC, then you can calculate the value of VCE. So this is how you can calculate IC and VCE. So here you can see that if there is any change in VBE, that will affect your IB, and then that will affect your IC, which is beta times, and the value of beta is very high. So in that case, the effect of temperature is very high. So in fixed bias configuration, the temperature stabilization factor is poor. So definitely we need to do something by which we can improve the stabilization factor. So here the concept is a fixed resistance RB is used to provide the biasing, which is connected with the VCC. So here in this configuration, you can see that there is a graph in between VCE and IC, which are our operating points. So these are the output current transfer characteristics. So here if we calculate the value of maximum collector current, which we can calculate by putting the value of VCE equals to 0. So in this equation which we have already calculated, if we put the value of VCE equals to 0, then the IC set can be calculated, which is VCC by RC, and this is the point over here. Similarly, we can calculate the cutoff point where the value of IC is 0, because it is in cutoff region, so IC is 0. So here you can calculate the maximum value of VCE, which is equals to VCC. So here you can see that if we join these 2 points, so we will get the load line. So this is the concept of load line. Any point which lie on this load line is known as operating point, but we have to ensure that through biasing that this operating point should be like that, so that we can get the maximum amplification. In case if this Q point lie in between, then we can get this much of amplification. But in any case, if this Q point shift over here like this, so at the upper side there is more scope for amplification, but the negative side there is very less scope to amplification. So that means there is a amplification like this. So we will get a clipped output at this jaw. So it is very much required to fix the Q point in the middle of load line. So using this fixed biasing technique, you can find the operating point. So second biasing technique is emitter stabilized biasing circuit. So here the emitter resistance RE is, additional emitter resistance RE is used. The concept is same. Here also you have to apply the KVL in this loop, so that you can calculate the value of IB, and then IB is related to IC with a factor of beta, then you can calculate the value of VCE. Here the value of stabilization factor is more, so we can prefer emitter bias technique over the fixed bias. This is another biasing technique which is known as feedback bias. So here you can see that a feedback is connected from collector node to base node to provide the biasing. The circuit arrangement is different. So in the previous one we have used this RE which provide the negative feedback. Here we have used another feedback which is connected from collector to base. So here this RB is the biasing resistor which we have additionally added to this circuit. So here also the stability is improved because of this RB, because it provides negative feedback. So if we add any negative feedback to the circuit, then we can improve the stability. So this is the better scheme. And this is the last one, which is voltage divider biasing technique. Here in this biasing technique, you can see that the circuit of this biasing, it is having two resistor R1 and R2, and at the collector node there is one resistor RC, and RE is connected like we have connected in emitter bias configuration. Input is applied over here and output we have taken from the collector node. For the DC biasing, the coupling capacitor are not used. So because these are the open circuited. So this is your circuit. So again we have to calculate IC and VCE from this circuit. So to calculate IC, basically we have to calculate the value of base voltage VB. So you can calculate VB from here. So at this node, if this is VB, so base voltage is equals to VCC into R2 upon R1 plus R2. This we can calculate with the help of voltage divider. That's why this scheme is known as voltage divider biasing. And we can redesign this circuit like this. RC, VCC, and when we have calculated the VB at this node, the R1 and R2, we can calculate the equivalent Thevenin resistance, which is RTH, and that is equals to R1 parallel R2. So here the equivalent circuit will be like this. This is VTH, which is equals to this voltage, and RTH. And here this is RE. So now you can see that the equivalent circuit which we have redrawn from the voltage divider biasing scheme is similar to the emitter bias configuration, where we have used a RE to provide the negative feedback. So in this scheme, because of the combination of R1 and R2, we get the more stability factor as compared to any of these biasing schemes. So now you can see that the one problem on voltage divider biasing. So for the previous circuit, if these are the value which are given to you, VCC, R1, R2, RC, RE, then we have to calculate the value of IC and VCE. Here in this question, the circuit is to be analyzed using the approximate method and the exact method. So for approximate analysis method, this is the condition: if the beta RE is greater than or equals to 10 times of R2, then you can use the approximate technique. But for the exact calculation, you have to use this circuit only. When we talk about the approximate analysis, in that case, you can overlook this RTH. You can make this RTH equals to 0, and then you can apply the KBL in the input and output loop. So here, if we check this condition is satisfied, then you can apply the approximate method. And for approximate method, these are the simple steps by which you can calculate the DC biasing voltage. Like we have already written the formula for VB, that is equals to VCC R2 upon R1 plus R2. So this is how you can calculate VB. VBE for NPN transistor is equals to 0.7, and VBE equals to VBE is equals to VB minus VE. So from here you can calculate the value of VE, which is equals to 0.94 volts. If you know the value of VE, then you can easily calculate the value of IE, and if you know the value of IE, then you can write IC is nearly equals to IE if beta is high. So in our case, beta is 140. So in that case, you can equate IE with IC. So you can calculate the value of VCE. So this is how you can calculate the biasing points or operating point for BJT. And in all these 4 biasing techniques, the voltage divider biasing provide the maximum stability. So this is all from my side for this lecture. In the coming lectures, we will discuss the MOSFET.